But since you asked, I'm not sure what your question is specifically. My intention here is simple. I'm not going to do the problems all the way. I think I'll present enough for you to finish them. And if that gives you enough information where you can successfully finish it, just repost your homework with the successful completion of the problems. Does that make sense? You understand what I'm saying? That if yours was not correct, I should be able to push you far enough along where you should finish, and then you can show me that you corrected your work. Is that okay? I want to make sure I'm not just talking into the air here. I want to make sure that I'm actually that you're actually listening and using this stuff. I have a bar of length L, and I'm asked to figure out the moment of inertia about different axes. And these are the three axes that were presented. This is a parallel axis theorem problem. So do you need the code still? Bringing joy one student at a time. All right, so parallel axis theorem states that I can find the moment of inertia once I know one of them. In this case, I know the moment of inertia to the center because it was proven in problem number 1, or hopefully it was. So if you proved it in problem number 1, or looked it up on a chart, then a moment of inertia of a bar about its center is 1/12 ml squared. So the rest of these are just moving it. So every one of these axes is parallel to that axis. So I'm looking at moving it to here. That's just a distance of L over 2. So I would have 1/12 ml squared plus m times L over 2 squared. Right? That's it. And next one, all right, plug in L. Not a whole lot there. Done. Now, the next one, you got to work for it. It's all that, I guess, Pythagorean theorem stuff. All right? That's all it is. A little L squared plus L over 2 squared. I'll let you guys dish this one out. But that's it. That's all number 2 is. So I think I've said enough. And it's not really... Perhaps let's go to another one. One where we might get a little bit more, something more interesting. So number 3. What is it about number 3 you want to know about? We already talked yesterday that there's probably a method for doing this problem that's better than another. Meaning, I don't know who asked for number 3, but what's the difficulty about this one compared to the one where we pulled the stick all the way to the side? Isn't the only difference in this case that we didn't pull it up all the way? Who asked? Somebody asked for number 3. Nobody asked for number 3? You guys did ask for number 3? Well, what do you want? What do you want to know? The very first what? Problem? No, okay. So the rod begins here. And what do I do with it? Okay. So 45 degrees, perhaps. And compared to straight down. So we moved it up 45 degrees. The pivot point is here. We're going to release it from here. So torque seems like the right place to start. If I want the angular acceleration, then net torque is going to equal I alpha. Angular acceleration seems to be implicit in this, explicitly stated in this formula. So I just need to figure out what the net torque is. I am pretty confident there's only one force causing a torque here. The exact same one we had yesterday for the exact same problem, except that in the case of this problem, we didn't pull it perfectly horizontal. So this is part of my concern, is that not everybody was really paying attention for the ones that we did yesterday. This is also 45 degrees. Yep.
I thought you had to do conservation of energy because the torque would be changing, or the...
If I want to find out how fast it's going at the bottom, I'd have to do that, but didn't ask that. It will in a moment. But right now, it just asks for the angular acceleration the instant it's released. So when it's released from this position, correct? Now, I agree with you wholeheartedly that when I plug this in, which is going to be L over 2 times mg times the sine of 45 degrees, that's going to equal I alpha. That when I release it, this acceleration is only for the instant I let go. That the moment I release it, that acceleration is going to cause it to accelerate, and it's going to change this angle. So this acceleration is for t equals 0 only. And after that, I don't know what the acceleration is going to be. I know it's going to be getting smaller, because when it makes it to here, the net torque will be 0. So yes, the acceleration is changing. And because of that, I could not use torque to figure out the velocity at the bottom, or probably anything else, like how long it takes to get to the bottom or anything like that. But I can use torque to figure out the acceleration. In fact, that's one of the things that in your decision tree that I put out there is that Newton's second law, probably the best way to figure out acceleration. It will be the fastest. Not the fastest way to find velocity. Even if it was a constant force, it's still not the fastest way to find velocity, because once you get the acceleration, you've got to find some alternate method to figure out how that acceleration caused a change in the speed of the object. So this will only give me the acceleration. And this is all you wanted, right? Yes, sir. I can. I don't want to. So I will be mean about it, Tanner. It's that formula, right? Every class period somebody's asked this, and it's made me mad, every one of them. So this one gets to be no different. I didn't finish this, by the way. You'll need to put a 1/3 ml squared in there to get alpha. But if I want to find the velocity, I would not be able to use the acceleration. I think we talked about this yesterday, but just to make sure, I would have to make my own motion equation to try and figure out what the motion of the object is, because this acceleration is changing all the time. And I don't want to do that when there's an easier method. Now, unfortunately for all of you, we will do this. We'll do this when we get to simple harmonic motion. We need a motion equation for things that oscillate. This thing oscillates, doesn't it? Let it go, it swings back and forth. So we'll have to do that eventually, but we're not doing it today. On the other hand, figuring out how high the object was lifted when we lifted it to 45 degrees, whatever this is, think we got a method for that. Something on the order of h equals, I'm going to use a different variable here just not to be confused, x minus x cosine theta. Don't want to get the L's confused here, because L represents the length, in this case, to the center of mass. So probably the amount of potential energy we have here would be L over 2 minus L over 2 cosine 45 degrees. And yes, you would use that thing, that equation thing. Were those the words you used, Tanner? The equation thing? Sorry, Tanner. You're the target. Are we good though? You can find the rest, right? So that equal to 1/2 I omega squared. This problem ultimately is the same as just dropping the rod horizontally. In fact, if you put in 90 degrees for this, you would have gotten mg times L over 2, which is exactly what you get when you lift it up. So it's perfectly horizontal. Done with 3, I think. You guys can figure out the details. Is there anything else you want to know there? Yes. Good job. You get a star for reading today. Tangential acceleration, 0. If you don't know why, I'll be happy to tell you. Yes. So I've drawn it, actually. The tangential acceleration when it's at the bottom of its motion. So the net torque equation still can be used here to figure out the angular acceleration. So let's look at the angular acceleration first. However, it has swung from this position to this position. So I need to look at the angle between the torque arm and the applied force, which appears to be 0 degrees. So 0 degrees, which means there's no net torque at the bottom. Right? When it's straight down, there is no net torque. There's nothing causing it to move side to side. That's why if I just hold it vertically, it doesn't start moving on its own. So that means alpha is 0. Well, the tangential velocity for any point, I'm sorry, not tangential velocity, tangential acceleration for any point along the length of the meter stick is equal to alpha times r, my position along the meter stick or my position along the rod. But if alpha is 0, the tangential acceleration must also be 0. Is that okay? All right. Then, so somebody said 4. Okay, 4. So I hope you can see why I'm doing this. I have a disc that I mounted on the edge. I pulled it up so that its center of mass was aligned with the pivot point horizontally, and I released it. So this is yesterday's problem and the other problems where we had the bar sideways, with the only difference is that now it's the moment of inertia of a disc about its edge, which might require me to find a new moment of inertia. So I'm going to find the moment of inertia of a disc about its edge and use it the same way I use the rod about one end, because that's all this is. Now that does mean knowing that the disc about the middle is 1/2 mr squared, and then adding to it how far I had to move the axis of rotation, which I think we can all agree is 1 radius. So now I have my new moment of inertia. It's still just mg. Can't really see that. Mg is the unbalanced force that is causing a torque on our object. But do you notice that this is now nothing different than the rod problem? It's just that any place where you had to put 1/3 ml squared, you're now going to replace it with 3/2 mr squared. But everything else is exactly the same. I'm not seeing the same kind of recognition out there. Am I wrong? Do you have a problem with what I just said? Somebody asked about number 4. I'm just trying to talk about it. Is that enough to get you to finish? All righty. Fun time. And 6 would be nice too. We'll start with number 5. And the reason is very simple. I told you first semester we were coming back to this. But you should have been super successful at setting this problem up. I should come and look at your work because you have your first semester notes. This problem is in there like multiple times. So let's start with what you know, because you should know a whole bunch about what to do here. I've got a pulley. I'll make it large enough where I can use it to exaggerate some things, like the fact that there is a string that's been wrapped around the pulley, like so, and hanging off of the pulley got a box of 2M and M, and away we go. So you were asked to draw a free body diagram that represented the forces acting on the masses and the pulley. I suspect tension upwards, weight downwards. Good. I suspect tension upwards, weight downwards. Good so far? You might have even gotten a little uppity and reminded yourself that it's probably going to go this way, and maybe you did a one of these. Did you maybe do one of those? I hope so. I mean, this is all stuff you've done before. Did you do that too? Because we've done these before. However, you were asked to just draw a free body diagram for each mass and the pulley. Now, for the pulley, you might be tempted to put everything at the center. I'd encourage you maybe to have a little diagram to the side just for objects that rotate. Some of the forces here are obvious, and some maybe less so. For example, did you make sure you put the weight of the pulley as a force? The pulley has mass now. There's probably something holding up all this mess. I don't know what the force on the pivot. Now, did you also draw that there's 2 other forces acting downwards on the pulley? Did you label them T? Does that look like what you drew? You understand there's a big problem here. And let's talk about the problem, but yes, sir?
I thought for a free body diagram, you don't have to dot. So where would the 2 T arrows go if you just had the dot?
I guess at the center.
So they would just be added on to the energy.
Sure. The problem with that, like we're going to find out right now, is we know the pulley doesn't go anywhere. It just stays there. Does that tell you the story of what the pulley actually does? I'm saying this, and I'm trying to be clear about something that might not be clear to you, something that you probably couldn't put together, which is why I put this problem on here, to let you know there's more that we have to do. We've been stuck doing the same problem for a week and a half, but there's more that we have to do. This is the first time where in the course of your problem, the pulley had mass. Correct? This one has mass. It didn't say it was a massless pulley. It said this is a pulley with mass, which means the pulley has inertia. Which of these four forces causes the pulley to turn? I see two tensions. And if you did them exactly the same way you did them before, those two tensions appear to be the same. There would be no turning that pulley if the two tensions are the same, because the net torque would be zero, right? Equal torque on both sides of your pulley, which should suggest something to you that the only way the pulley can possibly turn is if there's an unbalanced torque that would cause its inertia to change, or cause its position to change. It wouldn't do it on its own because the pulley has inertia and resists changes in motion. So this unbalanced torque can't be zero. Yep. Well, I know it's not 2 mg, because if it was 2 mg, then that would mean this tension would be 2 mg, and the net force on that mass would be zero. The only way that mass accelerates downwards is if the tension is less than 2 mg, right?
I'm thinking that like the torque of the whatever's going up the pulley is equal to 2 mg, and then the mass of the pulley.
I doubt it. No, because the center of mass of the system is accelerating downwards. So I don't think it pulls up with the whole weight. If it did, it wouldn't have the center of mass accelerating downwards. I understand your misconception, but no, this object doesn't have, this force right here does not have to support the weight of everything, because everything isn't sitting still. Part of it is moving downwards, accelerating downwards actually. So it wouldn't have to support all of it, which is why I know this can't be equal to 2 mg. It's another reason. So back to where we are, the piece of information you're missing, the thing that you need to change your thinking about, is that the tensions are only equal if the pulley has no inertia. If the pulley has inertia, then the tension changes across the top of the pulley, with this being, say, T2 and this being T1. They are no longer equal, which means we can't use just those two relationships to solve for the acceleration of the system. Now we are going to have to deal with the torque acting on the pulley, because it's experiencing two unbalanced torques. I'd probably argue that T1 has got to be less than T2. So that's probably new information. I'd make sure you write that down. This will be true about any problem that has a pulley. All of our Atwood machine problems, every one that we did first semester, and there was a bunch. Anytime there was a pulley, the only reason we said the tensions were equal, and you might not believe this, but we even said this in class, was when the tensions were the same. When the pulley has no inertia, the tensions can be the same. But if the pulley has inertia, that's no longer true. Which means, of course, that we have to now calculate the torques acting on the pulley, of which there are two. There's the torque from tension 2 and the torque from tension 1. Now, this opens up a whole bunch more stuff we have to think about, which is why I tried to say we're just scratching the surface first semester with this stuff. This is where the action really is. I don't think I have to remind you how to calculate torque, but I do want to realize that I have said that this direction is the positive direction. So I would say T2 provides a positive torque and T1 is a negative torque. T1 is attempting to rotate the opposite direction. Is that good for everybody? So moving on, torque is torque arm length times the size of the force times the sine of the angle, which is why a free body diagram for an object that rotates is somewhat meaningless. When it rotates, you probably need something to help you understand the extension of the object, to understand the size of the torque arm. Again, I know I misled you a little bit on number 5. I just wanted to make sure you understood that we were just scratching the surface. There's more to do. However, I am also, this is going to bother you, I am also expecting you to remember things from first semester. I don't want to hurt your feelings, but I have that expectation. So keep those notes. This torque arm length is R. So R times T2 sine 90 degrees. For a pulley, remember, it's always going to be 90 degrees. The string will always exit the pulley at an angle that is perpendicular to the torque arm. That's why we use pulleys. R T1 sine 90 degrees. So net torque equals I alpha. So RT2 minus RT1 equals I alpha. Okay. Now let's highlight the 3 equations that Newton's laws have created for us, because that's really the only difference, is that we now have one more equation that works in the inertia of the object. But if you were me and you wanted to make sure we highlight our problem, we have another problem, and that is, although I see T1s and T2s and stuff everywhere, this one has alpha in it, and these both have A in them. And in the prior ways we've done this problem, we've assumed the accelerations have been the same for both boxes. Meaning we said that if this box went up a meter, this box went down a meter. Do you remember that? But we've got an alpha in there now. So this next argument is something else I'm not sure you would have thought of. So let's see if we can rationalize this. Do you see a relationship between how far this box would descend and how far the pulley would have to turn? You understand what I'm saying? If not, maybe I'll say it differently. If the pulley turned one time, would you agree that the boxes would have to move one circumference? Does that make perfect sense? Because I want you to think. I'm going to write this in the bottom right-hand corner. We're trying to figure out if we can use this formula to put everything in terms of linear or everything in terms of angular. We have to ask ourselves if this formula works for this problem. So again, if it turned one rotation, that would be 2 pi. Do you think the box is going to move one circumference, 2 pi r? Does that make sense? Because if you think that's true, then you can immediately, and I know I'm erasing it, but this isn't rocket science, this part. We're just trying to say, can we do this? Can we use this thing? The thing that brings together the translational motion and the rotational motion, can we use that here? Because I think we can. I think the way this thing spins is related to the way the masses move. Moreover, they'll often say on a pulley problem something about moving without the rope slipping over the pulley. I didn't say it specifically in this one, but they'll often bring that up. That's what they're trying to tell you. And the reason that's important is it means I can write this as RT2 minus RT1 equals I times A over R. Now that might not look important now. Trust me, you have done the second most important thing here after making sure the two tensions aren't the same. Almost always, that single substitution is worth a single point on its own. In almost every rotational motion problem, you'll get 1 point for making this substitution. Make it big, make sure that the graders see it. even if the rest of your problem is all falling apart around you. Get this point. I'm going to continue, but I don't know that I'm going to get to the full end of the problem. And when I say continue, what I'm going to do is I'm going to put this up here small and maybe move it off to the side and just bring out the parts that are important. And in our prior dealings with these problems, you'll remember the parts that are important. These are the parts that are important. In the past, we only would have had these two things, and we would have talked about adding them together. Now, we've got these three things. The problem is that those R's are kind of in the way. Did you notice that? Let's get them out of the way. I'm just going to divide by R, because if I get them out of the way, do you notice now that if we add everything up, all the T's cancel? Do you see that? That if I add up the left side of this, I have a positive T2 and a negative T2. Those will cancel. And a positive T1 and a negative T1, those will cancel. So adding it straight down, I get 2mg minus mg. The net force. All right, this is the net force on the system. I agree. The other side, it's a mess. There's a lot of things I have to add up there. Let's get all three of them there. There's 2ma plus ma plus, I'm going to rearrange this, I over r squared a. I'm doing I over r squared. That's going to be obvious in a minute why. You notice that they all have an a in them, correct? Net force equals inertia times acceleration. You see it, right? We've talked about it before, but it's right here again. This is the net force part. This is the inertia part. This is the acceleration part. If I apply an unbalanced force, the object will accelerate. How much it accelerates depends on how much inertia there is. The only thing that has changed is that I have this portion of inertia that's due to something rotating. It's going to make it rotate slower. Notice I'm adding more inertia. By the way, what is the pulley? It's in the problem. What does it state that it is? It's a disk. Do we have anything that we could substitute in for a disk? And do you notice the r squared there? Can I do the substitution in my head? Because I want to. It's 1/2 mr squared divided by r squared. So I think you guys can kind of work on this a little bit. This is an Atwood machine problem with a heavy pulley. It has all the same dynamics as before. When we reach the end, the only actual thing we will see that's different is there will be something added in here that will represent the inertia of the pulley. If it were a ring, that number would be bigger. And trust me, that's a thing to do, right? Just like I changed the rod out for a disc and spun it about, they could change your pulley, make your pulley a solid sphere, a ball, a hoop. They don't care. They'll put whatever they want in there that spins. And, or it says ribbon. ribbon. We're not going to use ribbon. We're going to use toilet paper. So, I suspect you guys will agree that there are two forces acting on the system. There's tension and weight. Does that make reasonable sense? Okay, so net force equals MA. We want the acceleration. So I'm going to make downwards positive since that's the direction it goes. Is that okay? mg minus tension equals MA. Now, hopefully you're noticing the same thing I'm noticing, that gets us nothing, nowhere. We don't know what the tension is. How can we find A if we don't know the tension? And I didn't take the mass, but maybe the mass is, something I'll show up later. But we agree the thing is spinning and it appears to accelerate. So would you also agree that net torque must equal I alpha? Does that seem reasonable too? Now, here's the part that is going to be upsetting to some of you. Maybe not. Some of you probably don't care. But these are the only two forces that act. And if you don't believe why, did you notice that the toilet paper went straight down? You did notice, right? And you also notice that never was it like this on the way down. It was always perfectly like that. You notice that too, right? So when it unrolls, until it hits the bottom, it goes straight down, unrolling from the side. I'm saying that because there's no other forces that must be acting on it. Now here's my question to you. Where is it pivoting? You watched it, right? Is it pivoting about its middle, or is it pivoting about the edge? I mean, here's the thing. Different people in this room probably think different answers here. Probably just the way your brain works. And I can't tell you which one of you thinks which, but I can ask you. So raise one finger if you think it's pivoting about the middle, and raise two fingers if you think it's pivoting about the edge. Just hold them up. I see it pivoting about the middle. That's how my brain works. So in this room, wow, it looks almost evenly split, except for like half of you don't even have a finger up. Thank you. Just pick one. It's an A-B test, and you can't get it wrong because it's either one of them. In most cases where something's accelerating like this, you can probably pick either one. So which one do you want to do? Because I didn't get a clear idea. Want to go middle? We have sufficient time for only one of them. That doesn't mean that we couldn't try the other one later. Believe it or not, the answer is faster if you pick B, because it is. I don't want to tell you why it is, but it works just as well to pick A. Doesn't make any difference. So we're going to pick A. This is the direction of the acceleration. So net torque, I only see one. If I pick A as my pivot point, so I'm saying A is the pivot point. I'm being very clear about this. So if A is the pivot point, then the weight doesn't cause a torque. The tension does. Does that make sense? Because the weight's acting at the pivot. So my torque arm is R. So I will have R times T equals I times alpha. Would you agree that the acceleration of the toilet paper going downwards is related to the angular acceleration of the toilet paper? One rotation of toilet paper equals one circumference of unrolled paper. Okay, so RT equals I times A over R. It's a ribbon disc. I'm thinking disc. Looked like a disc in the picture I provided for you on the homework. So I'm thinking disc. Algebra. You doth heartless bitch. There we go. Bye-bye, all of you R's. And that will leave me with T equals 1/2 MA. But wait. I see a pathway to an answer. Do you see a pathway to an answer? You should take it. It's a nice little on-road. That will give you A in terms of G, like I asked. Yes, sir?
Does it matter that R would be decreasing with roller?
Probably in real life, it would matter. Luckily, we're using toilet paper, so how much is that R going to change? Not to mention, as the R changes, it takes some of the mass off with it. So it actually affects it even less than you might think. But we know R more important than M, because it's how far away from the center of mass the mass is. So it does affect the answer. More importantly, for toilet paper, it's not a disc. It's a disc with a hole in it. So for those of you who want to get accurate answers, we might have to figure out how big the hole is in the middle of the toilet paper. Because you'll notice, in this case, the R canceled out. But if you want a more accurate answer, you need to take into account the hole in the toilet paper. Yes, Tanner? Disc with the hole. It's a thick ring is what we treat it as. That's a disc with a hole. So we did not have a chance to talk about number 7, but I want to, as a departing couple of words, have you think about